Now we have derived the equivalent circuit of the induction machine. So there we have seen the parameters, the stator resistance, the leakage inductance, the magnetizing inductance, the core loss component, rotor resistance and rotor leakage inductance. So all of these parameters, how do you find them practically? That is what we use testing for. Okay. Now in reality, testing is in fact very complex, but here we will just get an idea of how the testing is done so that we can find these parameters at least approximately. Okay. So first we will start off with the no load test. In the no load test, you can get information about the rotational losses. So how is this test performed? Let us say this is the induction motor. You are going to have 3 lines, right, for the 3 phases. So each of the phase current you are going to measure using the ammeter, and we can use the 2 watt meter method to measure the power. Okay. So these are the watt meters. And finally voltage using the voltmeter. So this you are going to give to a 3-phase supply which has a variable voltage as well as variable frequency. So what are the 3 readings that you are going to get here? You are going to get the input power measured by 2 watt meter method. This you can take as P naught. Next you are going to get the line voltage. You can take this as V naught. And finally current per phase, which is equal to I naught. So each of the phase currents will more or less be same. That is what happens for a balanced 3-phase supply. But in case there are slight differences, you can take the average of the 3 ammeter readings. Now since this is the no load test, what is meant by no load test? This means that the rotor is spinning freely. No load is attached to it. Okay, so that is why we call it as the no load test. So what is meant by no load? The output power is equal to 0, but the motor will still take some power. So what is that power used for? It is used for the losses. Therefore at no load, power drawn from the supply is used for losses. So what are all the losses that you can see here? There will be stator copper losses, you will write as PSCL, plus the core losses. The magnetization is happening, right? So there will be core losses, plus friction and windage losses, and you can consider the stray losses as well. Now one doubt that you might get here is, we have considered the stator copper losses, but you have not considered the rotor copper losses. So why is that? If you remember the equivalent circuit, this is how it is. Okay. Now when there is no load, there will be very little current that is drawn by the rotor, but the magnetizing inductance will draw high current. A large magnetizing current is required to set up the magnetic field in an induction motor. So that is why the current through the stator winding, this will be quite high, that it cannot be ignored. That is why we cannot ignore the stator copper losses, but we can ignore the rotor copper losses. So this I1, this no load current, will be at least 30 to 40% of full load current. Okay, so this is an important point. If it is better, you can remember it. So this P naught will be equal to sum of all of these. Okay, and in addition, removing the stator copper losses, the remaining losses which are present, we can term it as the rotational losses, and we can find the rotational losses because the stator losses can be found out because we know the current. What is the stator copper loss? This will be 3 times I1 square into R1. I1 is the current flowing through the stator winding, R1 is the resistance of the stator winding. So I1 value you can get from this ammeter value. So if this is found, then we know P0, then we can find out the rotational losses. There is also a separate test to find out the resistance of the stator, so that we can find the stator copper losses. It is called as the DC test. So how do we do this DC test? If this is the induction motor, then these are the 3 lines for the 3 phases, right? Across 2 of the phases, we are going to connect a DC supply, Vs let us say, okay? And here we are going to connect an ammeter and a voltmeter. So here we have the ammeter and we connect the voltmeter here. So let us say the voltmeter readings and ammeter readings you are going to get as V0 and I0. What will be the value of V0? It will be equal to the supply voltage, okay? And here the resistance of the windings can be considered for a star connected induction motor. Usually it will be star connected only. So here we are not considering the reactance. Why is that? Because we are connecting a DC supply, and for the DC supply the inductance will act as a short circuit. It will not offer any impedance, okay? So this is the stator resistances of each of the 3 phases. Since we are connecting across 2 phases, this is the current, this is the path of the current flowing. So what will be the resistance encountered by it? 2 times of the each of the stator resistances, each phase, okay? So we are going to get the resistance 2R1 will be equal to the voltmeter reading divided by the ammeter reading. So from here you will get the stator resistance as V0 by 2I0. Okay, so this is how you find out the stator resistance, and this test is called as the DC test. What is the next test that we have? We call it the logged rotor test or blocked rotor test. Okay. So the no load test, it was analogous to the open circuit test of the transformer, and the logged rotor test is analogous to the short circuit test of the transformer. Okay. So here what do we do? How do we ensure that we are short circuiting an induction motor? Okay. That is by blocking the rotor. The rotor is blocked so that it cannot rotate, and then a voltage is applied to it. Okay. So if the rotor is allowed to move, then it will become an open circuit test, okay, no load test. But since it is being blocked, we call it as being analogous to the short circuit test. So how will the connections be? It will be same as no load test only, except that the rotor is locked. Okay, so we are going to have the ammeters of all the 3 phases, the voltmeter which will give the line to line voltage, as well as the power by 2 wattmeter method we are going to measure. Now how will this test be performed? Remember that the 3-phase supply is a variable voltage and variable frequency. Okay, so what happens is, since this is a logged rotor, the slip will be 1, S is equal to 1. That means the rotor frequency is going to be same as the line frequency. Why is that? Because the rotor frequency Fr is equal to Sfe. Okay, but under normal operating conditions, the slip value is going to be very small, so the rotor frequency will fall very small. That is the issue with logged rotor test if we do the test at line frequency, that means at 50-60 Hertz. Okay, this is the normal operating frequency that we give. Okay, so in order to replicate what will be the actual operating conditions, what is the actual operating condition? It will be the rotor frequency will be 2 to 4% of the line frequency under normal operation. So in order to replicate this, what we do is we perform the test at a lower frequency. Okay, therefore in order to replicate the conditions of normal operation, the test is performed at low frequency, usually of the range of 25% of rated frequency or sometimes even less. So this is one point about the supply that we give. Another important point is we give the voltage that is enough to get the rated current. Okay, voltage is adjusted to get rated current. Now, what will the equivalent circuit look like? So the equivalent circuit, we know the stator parameters will be R1, JX1. Next we have the magnetizing inductance, and finally the parameters R2 dash by S and JX2 dash. Okay. Now what happens is, since the slip is 1 here, this impedance will now be much lesser than the magnetizing reactance. So all of the current will flow through this R2 dash by X and JX2 dash. So you can ignore, in the locked rotor condition, you can ignore this Xm. Okay, can be ignored since R2 dash by S plus JX2 dash provide a low resistance path. Okay, so what are you going to get? You're going to get a simple impedance, two impedances in series. So what will be the equivalent resistance that you will see here? R1 plus R2 dash by S, which is equal to R1 plus R2 dash. Why is that? Because S is equal to 1. And what about equivalent reactance? X1 plus X2 dash. So how do we find this out? From the obtained readings. What are the readings that you're going to obtain? You're going to get the power reading P0, V0 and I0. So in order to differentiate from the open circuit test or the no load test, we will write this as PBR, VBR and IBR. From these three readings, what can we get? Can get the power factor and the impedance. How to get? The power PBR will be equal to √3 times the line voltage VBR and the line current, which is same as the phase current in a star circuit. So it will be same as the reading that we are going to get, into power factor cos phi. So this will give you the value of power factor as the value of the power reading divided by √3 into VBR IBR. What about impedance? This will be equal to the ratio of the voltage and the current reading. So this will be the impedance value. Once you get the impedance and the power factor, you can find out the resistance value and the reactance value. How will you do that? R equivalent is equal to Z cos phi and X equivalent is equal to root over Z square minus R equivalent square. You can find out. Okay. So this is how you can find out the equivalent resistance and equivalent in reactance from the locked rotor test. Now R equivalent is what? It is equal to R1 plus R2 dash. From here you can find out R2 dash is equal to R equivalent minus R1, since R1 can be found from the DC test. Okay, since R1 can be found from DC test. But X equivalent, you cannot find the individual X1 and X2 dash. You cannot find them individually. Okay, because there is no test to find out X1 separately. So from the readings, what we have found out? We have found out the power factor cos phi, the impedance Z, R equivalent is equal to R1 plus R2 dash we have found out. From here we are going to get R2 dash as well, because R1 can be found from DC test. And what about reactance? Only the combination you can find out. But remember, this is at 25%, or you can say at test frequency. Okay, at test frequency, which is approximately 25% of rated frequency. So how do you find out the reactance at rated frequency? Because the reactance is a function of the frequency, omega times L, right? So at rated frequency, X equivalent rated is equal to the rated frequency divided by the test frequency into the value of equivalent reactance that we got from the test. Okay, so this is how you find out reactance at the rated frequency.